It's really a pleasure to be able to introduce Max. Anyone who knows Max knows how warm and welcoming and you just want to hear what he has to say. And so it's really a pleasure to have you here again, Max. Max did his undergrad, I believe, in physics at Cambridge. Yeah. Followed by then he made the transition from physics to more directly into climate change, really. He did his PhD at the Potsdam Institute for Climate Impact Research, mostly looking at the physical, effects of climate change and impacts in particular on socioeconomic systems, but also started to look at the potential for looking at impacts on natural systems as well. After his PhD, he did a short postdoc also at the Potsdam Institute, and then was awarded a prestigious Marie Curie Fellowship, an EU-wide fellowship to do a postdoc at the Barcelona Supercomputing Centre, which if you haven't spoken, if you don't know anything about it, it's worthwhile speaking to Max about it. It sounds like a really interesting institution to work, really multidisciplinary, really encouraging lots of collaboration, including just how they set up their buildings. For a number of years, Max has been looking at not only the impacts of climate change, but also attributing those impacts directly to climate change when there are other potential drivers. And so that's been a feature of his work, both in socioeconomic systems and more recently in ecological systems. Max, really looking forward to it.
Thanks so much. Thanks, Simon, for the introduction, and really nice to be back, seeing what many faces presenting on this topic. As Simon mentioned, most of my background is on climate change, the physical aspects of climate change, and looking at impacts, particularly of weather extremes. I was really lucky that it was about 2 years ago I was here for 3 months, and that sort of kick-started collaborations with Tatsuya and James on how to apply some of the methods that we've been typically using in a biodiversity context. So, I'm going to give you a talk today that's centered around this piece of work that Tatsuya and I have been doing, which is focused on birds and heat waves. But hopefully more broadly, it's going to fall under this umbrella of how to attribute impacts on species to climate change. And what that really means will hopefully become clear as I sort of introduce the talk. So I'll start super broad with sort of where are we in a climate change picture. I'm sure you're all kind of aware following these kind of phenomena, but if we look at sort of last year, 2024, pretty exceptional year, first year that global temperatures exceeded 1.5 degrees, this sort of Paris optimistic targets. It's just 1 year, but still an indication of the extent to which climate change is continuing and particularly accelerating. Actually had a lot of climate scientists a bit sort of dumbfounded to some extent, particularly this latter part of the year where you can see how much it's exceeded previous warming trends. Particularly, normally we get very hot years where there's an El Nino, and we saw these high temperatures persisting after an El Nino. And there's been a lot of debate about is this just internal variability of the climate system? Is it a new accelerated period of warming because of changes in feedbacks? It's not super clear yet. There's debate going on there, but it's an interesting time, and it's obviously just part of this continuing phenomenon of climate change that we're all familiar with at this global level. It's not just a global thing. Obviously, this phenomena then has many different manifestations at the local, the regional level. And I just wanted to highlight this. This is just based on data from Copernicus, one of the sort of standard climate data sources presented by The Guardian, looking at the places on Earth where last year there was a month that was hotter than had ever been observed in that location. And it's 65% of the world's surface, and global land area is a fairly substantially higher proportion. So it's kind of obvious if you get an abnormally hot year, you're going to get abnormally hot regions. But just really to point out, what this means, climate change in this way, is that we're getting unprecedented conditions at the local level, unprecedented climatic extremes, and obviously for societies, but also for natural systems, this is where we would expect to be starting to see some kind of impacts. And that's kind of what we're going to be looking at today. So, like I said, I don't have a background in ecological systems, but I did study a little bit of earth sciences and geology in my undergrad. And so for me, when I start to think about climate change and biodiversity, I always find it helpful to have a kind of geological context here, which I just want to share with you kind of briefly, because I think it's quite interesting. So we know in Earth's history, there have been lots of different periods where we've had extinction rates much, much higher than what we would typically have in geological past, sometimes referred to as sort of like mass extinction events. And from a mechanistic perspective, we also understand why those events should be connected to changes in environmental conditions. This was just a nice study from a few years, really showing that very clearly, just how across these kind of events, rates of extinction just correlate quite clearly with the magnitude of global temperature change, but also with its rate. And for me, this is a helpful way to put the modern context into perspective, because if we think about the 1 degree that we've had over the last 100 years, that's about 10,000 degrees per mega year, which puts us sort of 2 orders of magnitude off that scale there. Given that these are sort of all mass extinction events that in the geological past, where like 50–60% of species have gone extinct, it tells us a little bit about the kind of the system change that we're experiencing. But obviously, we don't want to just have a geological perspective. We've got a modern perspective, and there's lots of excellent work that's going on about understanding how different species are sensitive to their changing environmental conditions, what impacts they're experiencing. This is just an example for amphibians based on the recent IUCN Red List assessment, and showing the different drivers of extinction risk in, this is 1980 to 2004 on the left, and then 2004 to 2021 on the right. And we can just see, this amplification of climate change effects in this recent period and driving effects for amphibians. And that's something we can see across different species groups, different ecosystems, that the climate change is potentially playing a larger role, and species are definitely vulnerable to these changing environmental conditions. That's something I think we probably understand quite well. But what I would say, and when we've been working on this stuff with Tatsuya and James, what we thought is a bit more of a knowledge gap is really to understand, well, if species are sensitive to their environmental conditions, well, what's actually the consequence of the long-term climatic changes that we've seen for those species? Yeah. And I think there we don't have such a strong understanding of what those long-term effects might be. And in particular, if we start to consider the effects that have really been driven by the human component of climate change, the anthropogenic contribution to climate change. And this is where we start to get towards this question of attribution from like a climate change perspective. And that's what our study is going to be trying to address today. And just to give us sort of a conception of what this means, it's really thinking about all the way from, say, human emissions through to changes in the environmental system through to impacts on species. And it's really along that sort of impact chain that we want to try and map out these effects to have a sort of attribution statement. Okay, so fortunately, I got to know Tatsuya, got to know James, and we're going to be, so I didn't get to know sulfur-crested cockatoo, but we're working on tropical, well, birds in general. That's the context that we're going to focus on in this study. And just to give you a broad outline of our approach before we go into the details, we wanted to start with sort of an empirical-based approach. So really looking at observed responses of birds to changes in their environmental conditions. Maybe you could contrast that with other approaches that people take in ecological and climate change literature that's quite popular, like species distribution models. They're a bit more theoretical. But we wanted to stick to sort of a data-driven empirical approach. What's a little bit different about our approach as well is that we really wanted to focus on the interannual variability of exposure to weather extremes, exposure to climatic conditions, and the interannual variability of how the bird populations are responding. And that's a little bit different from what I think most studies would do, which is looking at long-term trends. And I think a strength of this focus on interannual variability is that the year-to-year fluctuations in weather are much more sort of quasi-random, particularly from the perspective of the bird population, which means you've got much less scope for potential confounders compared to when you're looking at long-term trends across groups. And that gives us a better context for a plausibly sort of causal interpretation, I'd say, which we can talk about more. Another thing that we want to do is not just focus on average climate change, but focus on extremes, part of the motivation that I discussed earlier, but also James has done a lot of work on arguing as to why climate extremes should be one of the places where we expect most impacts. And then, finally, we're going to try and build this actual attribution framework, which tries to connect us all the way back to the human-driven component of climate change. So we're working with birds, and in that case, for our data, we went to the Living Planet database, one of the sort of, I'm sure you're familiar with it, global assemblage of time series of long-term monitoring of bird populations. There's obviously, as with many ecological data sets, there's quite big gaps, particularly in the tropical realms. But we've got a decent coverage across different continents, different biomes. I think we've got about 3,000, a bit more than 3,000 observations in the tropics, about 90,000 in total. So it's really not as much, but it's a decent amount to be able to see something with. Obviously, we're not just, in the context of looking at climate change, there's other drivers Simon pointed to. So it's important that we control for, look at the effects of direct pressure from land use change and human pressure. We do that with a sort of quasi-human footprint metric. It's not quite the human footprint metric because we wanted to have data going back as far as 1950 because we've got population data going back that far. So we just look at the land use and population components, not at the more complex elements like infrastructure, night lights, these things, because there's not data going back that far. And then we're going to look at changing climatic conditions. Yeah, that's our main point of focus. If you're not familiar with it, this is the ERA 5 reanalysis database we use, which is kind of like state-of-the-art assessment of historical climatic conditions, combines ground-based observations, satellite observations, and quite complex interpolation modelling techniques to provide like the best assessment of what was the temperature, precipitation everywhere on Earth at quite high spatial and temporal resolution, and it's a really good data product. And yeah, we're going to measure average conditions, average temperature, total precipitation in a year that these bird populations experience, but we're also going to try and look at extremes. And our framework for doing that was we looked at, say, an individual bird population that exists at a location, looked at the distribution of temperatures that they say have experienced in the early period from 1940 to 1970, sort of before there's been widespread climate change, and used just like a percentile to define a local threshold that we can say that's like a hot extreme for this bird population. There's different ways you could do that, and we test some sort of robustness to different ways of doing that, but it's quite a nice simple approach. This is what those thresholds look like. As you see, there's like quite the expected geographical pattern. And then this is what exposure to those extremes looks like across bird populations over time. So it's in each year how many days have exceeded those temperature thresholds, and it's aggregating over the populations that we've got here across different sort of latitudinal zones. So red is the tropics, orange is the mid-latitudes, blue the high latitudes, and everywhere there's this sort of increasing exposure, but really particularly in the tropics, we've got this really magnified nonlinear increase about tenfold, from about 3 days per year up to about 30 days of these temperature thresholds. The reason for that is essentially that temperature variability is lower in the tropics. So when you get a shift of the temperature baseline, more days get tipped over those thresholds into extreme units. But this is really just the setup, looking at the data, looking at how the exposure is changing. But what we really wanted to do is build a proper modelling framework that relates how the interannual fluctuations here, which are much noisier at the population level, this is aggregate, how they relate really to the fluctuations in bird population abundance, to really have a proper modelling that can connect these two. We've got data from multiple populations across time, so it's kind of a typical sort of longitudinal database context. And we use a mixed effects modelling approach to then model these relationships. Our basic structure is to have random intercepts at the level of populations, so that we're then just focusing on like the temporal dimension really, where we explore higher taxonomic groups as well. And then we're going to use fixed slopes to explore how the average population is responding to different drivers. We'll have human pressure, different climatic variables, and explore an aggregate average response and see if we can see a significant effect at that global population level. But obviously there's differences across populations, so we're going to try and explore heterogeneity as well, using interactions across a number of dimensions and lags to explore some of the dynamics. So I promised Matt I'd show an equation. So we've got one to describe the rough sort of modelling structure, where we're going to be looking at changes in the logarithm of abundance for a population from one time period to the next, time period being year. It's going to depend on the population level in the prior year, so a basic ecological dynamic, and we see that's really important in the model. Bigger populations grow more slowly. Going to also control for human pressures and how that's changing over time, and then also look at the effect of different climatic variables. And this would be a simple case of just temperature, but I'll show you it gets a bit more complex. We'll add different ones and add interactions. We've then got our random intercept at population level, and even also a sort of an additional test, and it's quite an important one this to test, I'd say, is also using a random slope with between the population and time. And that really means that we take out any long-term trends in the data, and it means that we can be really sure that we're focusing on these interannual fluctuations with which we have a sort of more plausibly random treatment and a more plausibly causal interpretation. Just to touch on this a bit again, because we had some discussions about this in the review process, and I come from an economic statistics background where everyone's like, you have to like defend that your model has a causal interpretation, but I know it's like a bit different across disciplines. So I think that the two bases for having this plausibly causal interpretation is the random exposure, but also the lack of a reverse causal mechanism, So there's not really a way that at interannual timescales, a bird population fluctuating can affect the temperature extremes that they're being exposed to. So once we see something significant, even if it's an aggregate response, it's indicative of an effect going in that direction. Good. Okay. So we can start to get into some results. They'll start with a table, so I'm really sorry about that. But I thought it's important because I wanted to take you through some of like the modelling steps. But it's super ugly, I know, and we'll have figures as we go. But I think it's actually kind of helpful. So we're always modelling the abundance growth rate, and we're looking at effects of different drivers here. Yeah. So our basic control is this abundance in the prior year, and we see the significant negative effect, this density dependence of the growth rate. We also see a strong negative effect of human pressures. So increasing human pressure, reducing the growth rate of bird abundance. And when we started analysing the climatic conditions, yes, I can do this actually. No, I'll just use my hand. We started with just looking at annual averages of temperature and precipitation, a sort of basic setup. And we can actually see some negative significant effects of warming on bird populations in general, nothing for precipitation. But what was interesting is that once we started adding and accounting for these extreme metrics, the heavy precipitation and the high temperature extremes, we see substantial effects of both, and it really sort of causes the average conditions to drop out of the model in some sense. So it essentially indicates that most of the impacts that we see in these populations are being driven by the exposure to extremes, not by the changes in average conditions. This last little term here is an interaction term, which we'll talk a lot more about in a second, so you don't need to worry too much, but that essentially is an interaction between heat, exposure, and latitude. So we see a strong difference between different populations on their geography. Bigger effects, more negative effects in the low latitudes. The rest of the tables sort of different robustness tests, and we've got more of them in the paper, but different things that we do is like changing the random intercept structure based on different taxonomic groups, doesn't really change anything. Accounting for spatial autocorrelation, because our weather variables are spatially correlated, it's an important step. Also for autocorrelation within taxonomic groups as well, because there might be some dynamics there that cause them to behave similarly. And yeah, we did some kind of fun placebo tests. If you're nerdy and you like the modelling stuff, these were kind of cool, but we won't talk about them a lot. Essentially to confirm that we're not just picking up a signal because of this long-term increase in temperature extremes. So we shuffle the data a bunch of ways and show that you can't get these kind of results unless the data is actually like ordered in the way that it is. Good, so we can start to talk about these heterogeneity of these heat extreme impacts, because yeah, across all these different tests, it was really the heat extremes where we kept seeing the strongest effects across all these different modelling specifications. The precipitation would sometimes be there, sometimes not, but the heat extremes really consistently. So we'll start with heterogeneity across like the geographic dimension, spatial dimension. And I mentioned that we have this model with a latitude interaction. So this is our basic geographic descriptor, which on the y-axis, we're looking at the impact of heat extremes on the growth rate. So we see how this varies with latitude, much more negative in low latitude regions, up until about 55 degrees north or south, beyond which it's, yeah, maybe even plausibly positive based on that linear interaction. I think an important note is that, yeah, below 55 degrees north or south is about 80% of the global land area, which is the histograms underneath in blue. So implying that based on this model, most of the global land area is in a regime in which increasing exposure to heat extremes have a negative effect. But we can also look at it based on biomes, a sort of an alternative way to describe that. This is quite like an aggregate biome level because we don't have sufficient detail to go into like more specific groups. So we did it at this kind of level, at which we see, yeah, very consistent effects across that tundra, boreal, temperate, Mediterranean. They're quite consistent with the latitude interaction, but the tropical realms are actually much more sensitive than what we get based on our latitude interaction. And the reason for that is essentially that we just don't have as many observations in the tropics, like we saw before. So when we try and estimate that heterogeneity with a linear function, it biases away from the tropics because we don't have as much data there, and means that we underestimate the effect of these kind of low latitudes. Okay, so that's the geographic dimension. Obviously, as well, bird populations are going to have different responses based on what species they are. You know, they're going to have different life cycles that are going to mean they're vulnerable in different ways. So we do a more full breakdown of this in another context, where we go at the level of bird orders, and re-estimate a response for each. But it gets a bit challenging in terms of the data constraints. For the Passeriformes, like that's dominant birds in our database, we've got like 60,000 observations for them out of about 90,000. So for them, we estimate this very similar response here in red compared to the baseline model in black. And then across different order groups, we see significant effects that are consistent for about 4 to 5 other order groups, There's one group that we see like an opposing effect, but they're actually a group of water birds, which we were kind of surprised that they were in the database. We think it might be like a living planet, bit of an area in their classification, because we wanted to focus on like terrestrial birds, and you have a separate source of freshwater ones for others. And then in a bunch of the others, it's like we've maybe only got 500, 200 observations, and not really enough to get anything significant. So we sort of aggregated all the other populations that aren't Passeriformes, and that gives this blue curve, which is broadly consistent in the sense of significant negative effects at lower latitude, and this kind of slope latitude, but like, yeah, a bit of a shift, different latitude at which you get positive and negative effects. Another interesting heterogeneity that we wanted to explore was the difference between migratory and non-migratory bird populations. One reason for that is that, so we're seeing these responsive populations to heat extremes. We can't really, it's hard for us to say whether they're dying or are they moving. We're not tracking individuals, so unfortunately we can't really shed too much light on that, but we thought that by distinguishing between these two types, we might be able to, see some different dynamics if these birds are birds that typically move a lot anyway. We don't see much of a difference between them, which is quite interesting. Still, it's kind of hard to interpret exactly what that means. But there's definitely, even though there's more data for the migratory birds, there's less certainty in the estimate, even though it's very similar. Which are kind of one interpretation there is that these bird populations that are migratory, they're going to be visiting many different locations, but we're only measuring their abundance at one place, and we're only measuring their temperature extreme exposure at one place. And so it's probably going to be harder to get like a proper good estimate for their effects, but it does still seem like the temperature exposure in the one place where they're getting measured is having a similar effect as with these other birds. Okay, so that's it for heterogeneity, and then finally with some dynamics, we look at how these effects play out over a number of years. It could be that there's sort of a recovery response, some different dynamics there after an initial negative effect, but we actually, if anything, see accumulating effects over time that could imply some maybe internal ecological dynamics that amplify the effects over time during initial exposure. Good, so that's sort of the basic first part of our modelling framework, which is building this model based on the historical data of how the birds actually responding to heat extremes, how does it differ across different places and across different populations. What was then really interesting, what I thought was really interesting and what we tried to do was to build an attribution framework which could essentially answer the question. We know that birds are sensitive to heat extremes. We know there's been this really strong intensification of heat extremes. What would have actually happened in a world where that hadn't happened? Yeah, in a world without that intensification, without the human-driven intensification of heat extremes, without climate change. So to do that, I think probably the broad things that one would need is an impact model for which you've got like a plausibly causal relationship, something that's not confounded by too many other things. So we think we fulfill that fairly well. Then an assessment of what's actually been the human contribution to these climatic changes. So yeah, there's some climate science methods that will come in there that I'll talk about in a second. And then based on that, we can generate counterfactual scenarios to say, this is what we think would have happened for the birds without climate change. So for this second part, this assessment of anthropogenic contribution to climate change, there's a number of ways one could actually do that. The sort of traditional way would be to use physical climate models and to simulate them under scenarios of increasing greenhouse gases and constant greenhouse gases and then compare them. We don't actually do that in our case because there's also been a lot of work recently on using just observations directly to do that attribution, a kind of data-driven attribution framework, which I'll just explain to you briefly now. If you're interested in climate science, it's kind of interesting. So the framework here essentially goes that global temperatures, global mean temperature, is entirely attributable to human influence and human emissions in terms of its long-term change. We can say that we know that well based on the climate science. So we can therefore use global temperatures as a proxy by which to extract the changes in local conditions which are connected to the global phenomenon of climate change, connected to global temperatures, and therefore connected to human emissions. So this is what this would look a bit like in practice. In black here is the actual observed temperature extremes at a given location, historically from 1940 to 2020. And then in red is shown the proportion of that which is correlated with global temperatures using like a Poisson model to model this kind of count data. So we can then use this red curve to essentially say this is the component of heat extreme intensification that's due to human emissions, not just, because I mean, look, you can see there's this crazy internal variability where you've got a year in 1970 with massive exposure, which is obviously nothing to do with human emissions. It's due to the internal dynamics of the system. Great, so if we've got this assessment of the anthropogenic contribution, we can then start to build a counterfactual by combining that with our impact model. That gives us a sense of how much the anthropogenic changes have contributed to impacts. Yep. And that's impacts on the growth rate. We can then subtract that from the actually observed growth rate. That gives us a counterfactual growth rate for the birds. And if we then accumulate that counterfactual growth rate over time, we also have to account for the density dependence, which is a bit nuanced, a bit complex, so I won't go into too much detail. But that will then give us a counterfactual abundance time series for the birds. So at the end of this, what we'll want to have essentially is two time series, one that's the actual observed abundance of birds over time, and another one that's the counterfactual scenario. And then we can look at the difference between those two as a percentage to say this is the percentage by which the abundance has changed because of climate change. Okay. And then, yeah, finally, we're going to do a bunch of Monte Carlo sampling to capture the uncertainty from these different sources, from the impact model and the attribution. Okay, so we can look at what these results start to look like. This is for heat extremes. This is looking at the difference between that observed and counterfactual abundance time series in 2020. So it's all the impacts that have accumulated from sort of 1950 or so up until 2020. And it's the percentage change, which is the difference between the observed and counterfactual. We can see across tropical realms, they're pretty big, over 30% in a number of cases. Smaller as we get further north, which is a result of both this latitude interaction in the statistical model, but also the fact that heat extremes are just intensifying more in the tropics. And then at very high latitudes, even some potential benefits for these bird populations based on our model. To show these dynamics over time, we can also just sort of aggregate across populations, again, within different latitudinal bands, which is what I'm just going to show here. So again, red is the tropics, mid-latitudes, high latitudes. This is for heat extremes, and we can see how these impacts have grown really from 1980 onwards, which is when this intensification of heat extremes kicked in. And on average, this is the median across populations for the tropics. It's reductions of close to 40%, and that's kind of the spread based on our Monte Carlo sampling of the different error contributions. In the mid-latitudes, it's much smaller, about 5%, and at the high latitudes, pretty much negligible in the aggregate. We've even got these positive effects. So we've been talking a lot about heat extremes, but in the statistical model, we did have a precipitation extremes term, which did have some significant negative effects. So we can run that through. And I think this is quite an interesting thing that we see coming out of a lot of these kind of climate impact studies, is that even if it plays a role in the dynamics of the system, the attributable impacts are really small, really, really small. And it's essentially because the human signal in the thermodynamics and in the temperature is a much stronger signal than in the precipitation component. So the heat extremes really dominate the effect. And if we look at the overall contribution of both as a climate change signal, it's just temperature extremes. One final thing that we wanted to do was we also had a human pressure metric in our model. So we wanted to try and construct a similar counterfactual with the changes in human pressure. So say what would have happened if human pressures, if land use and population had stayed the same as in 1950. And we can then evaluate these effects across our bird populations, which again, it's not representing the whole of the globe, so that's quite important to interpret this human pressure. But we see about 10% reductions across the tropics, 20% at mid-latitudes, and fairly negligible at high latitudes. Although, like I said, it's important to note that for human pressure in particular, the sort of scarcity of our observation becomes a bit more problematic, and also a lot of degradation of habitat happened before 1950, particularly at the high latitudes. But what's interesting is that if we put these together in the tropical realm, for the populations we've observed, the effects of climate change appear to have played a more substantial role than direct pressures from land use, which for us was kind of surprising. There's many limitations to that conclusion in particular, I would say, but it's still, for these populations we observe, for our modelling framework, that's what we see. That's quite interesting. This is just to say there's a distribution across the population. So in the tropics, some suffer more, some suffer less. Pretty simple as you'd expect. We're short on time, so I'm going to jump through. This is just to say that we test our attribution framework across some other kind of ways of doing it. So instead of correlating with global temperatures, we do like a resampling, where we say, what if temperatures are just kept kept being drawn from the distribution from 1940 to 1970 and continued like that as an alternative way to do it. And we get very similar responses. It's much noisier, but the magnitudes are very similar. So that's a nice sort of sanity check. And yeah, with that, I'll come to the conclusion. So we've got enough time for questions. Yeah, this I think is the first kind of conclusion from our historical modelling, is that for the birds, from what we can see at a global level, heat extremes are really playing a dominant role in terms of their impacts, more so than changes in average conditions. I think one interesting implication of that is also thinking about how species distribution modelling is done, that it's normally done with average conditions, maybe over seasons, but yeah, seasons and years typically. There's not normally the accounting for these kind of shorter term effects. I don't know to what extent that will be important, because they'll be correlated to some extent that suggests it might be worth thinking about. There's obviously a heterogeneity, and we see this strong signal that there's much bigger effects in the tropical regions. That's quite consistent with some of Tatsuya's earlier work on water birds and their sensitivity to average temperature change. And it's also kind of consistent with some of the other broader literature on biodiversity and its sensitivity to climate change being stronger in the low latitudes. Then finally, I think what's really new that we've been able to do here is do this attribution framework, which says, yeah, how much lower is the abundance because of climate change today, essentially. We get these fairly large numbers from, this is a range across different statistical models that we might have used. And yeah, also this conclusion that they're larger than the impacts of direct land use, at least for the populations we've observed here. So I just want to highlight a couple of ongoing pieces of work. With Simon, we're trying to run a similar type analysis for freshwater fish with Hara Friedlander, which is going really well, enjoying doing that. And also trying to do some work applying this attribution framework in a slightly different impact modelling context with some people back in Europe looking at comparative extinction risk models and tree extinction risk and drought in that context. So yeah, I find it a really exciting topic because not many people are doing this attribution stuff in the ecosystem context, but there's so many ecological data sets, there's so much ecological expertise. I think there's a lot of scope to apply these kind of things in different contexts. So if you're someone working on those systems, if you've got this kind of data, you're interested in those questions, really please get in touch, and I'll be really happy to talk and see if there's scope for collaboration. So thanks very much. We'll leave it there, and yeah, looking forward to questions. There's two online, maybe, aren't there? Okay, that's what I think. Yeah, go for it.
Great presentation, really impressive work. What I'm curious about is when you look at tropical systems, is that correlated, and how can you maybe pry it apart from warmer systems? So when I think about myself, and my how I deal with heat, so I know I come from a Mediterranean, Middle Eastern climate, and I know that if something's going to kill me, it's going to be the heat in the summer because it gets so hot, and it's not going to be a cold winter where I live. So I'm worried. I'm wondering about, let's say, bird species. When you're talking about tropics, could that also could that be true for all warmer climates, or how do you separate those two?
Interesting. So mainly the question about distinguishing heterogeneity based on the prevailing local climatic conditions rather than the geography and the latitude. So saying species might respond differently because they're already hotter, not because they're just at a lower latitude. Kind of that's the gist of the question.
Correctly, I'm just when you talk about how do you pry apart the tropics from other hot places?
Other hot places, yeah. Well, in some sense, we don't. When we explore the heterogeneity, let's say in this figure, we're really looking at it based on geography. So places in tropical regions, that's tropical regions as they've been labelled by the Living Planet database, and low latitude regions, that's low latitude regions in the sense of really does the population just sit at north of 21 degrees north or south. So it doesn't necessarily mean they could be up a mountain, actually. That's very true. So it's an interesting question, and a lot of the other literature on impacts in other contexts, actually, in socioeconomic contexts, that does these kind of modelling frameworks, that's often something that they would actually do as well, is that, say, try and describe that heterogeneity based on temperature rather than geography. So yeah, it's a good question. It's maybe actually something we should think about exploring and incorporating into it to test both. One thing that's true is that, and makes it a little bit problematic, is that when we talk about describing these heterogeneities, we're describing differences across the responses of different populations. And geography and temperature are just really correlated, like latitude and temperature are so correlated that it's very hard to disentangle that. You don't have like a good framework for identifying like a causal impact, as I kind of described with the interannual exposure, because like that's a very nice, there's no way human pressure is like fluctuating in the same way as temperature extremes from year to year, but yeah, across space, temperatures and latitudes are really correlated. So you can put them in a kind of horse race in your model, stick both in and see what comes out as more effective. But my assumption as well is that then, because they're so correlated, even if this was being driven by average temperatures rather than latitude, you'd still get the same kind of effect. You describe the same heterogeneity, but just with a different variable. And then when you end up doing this kind of attribution analysis, you should get a fairly similar thing. That there would probably be differences, but I think they would be minor. So it's interesting from the understanding perspective, and I think probably you're right, actually. It's more likely that the mechanism there is temperature rather than, it's not like I suffer more just because I'm at 0 degrees. Yeah, it's 5 degrees north. Like no one cares if they're at 5 degrees north, right? It's because I'm hotter. So yeah, that's good point.
Is there desert in that figure?
In this one, in terms of
the one you referred to before, where you have
this one,
tropical, yeah.
Yeah. So Living Planet database provides some very disaggregated biomes, and there's a desert and like xeric shrubland biome in there. But there were just too few observations in that for us to get like a proper estimate, which is why we ended up doing this kind of like these grouped estimates.
So it'd be really interesting to add that data to that database.
Yeah,
how it fits in.
Yeah, definitely. Yeah, I think with this we wanted to just get this kind of like broad top-down approach to test this kind of modeling framework as well. But there's 100%, there's a lot of so much to explore in terms of, particularly in the heterogeneities. And I think that's where also I'm quite limited, because I'm not an ecologist and I don't understand the different dynamics of why these populations would respond differently. That's why it's nice to be here as well. Like to actually be able to work with, say, Tatsuya, Simon, and yeah, get their input. Cool. Right in the corner, I think was first, right? Behind that. Yeah.
Yeah, my question was like when you talked about the baseline and threshold to quantify your extreme heat days. Like nowadays there's a discussion in the school of thoughts of shifting baseline and maintaining the standard threshold that we are considering now.
Yeah.
Like till the end of the century or like till later or like going behind us. Like what are your thoughts, and like did you use the same baseline or like that?
No, great question. Yeah. So we use a fixed threshold, so it's fixed for the whole of our analysis. But yeah, that's a really interesting question. In the socioeconomic context, people talk about this a lot, and there it's often related to the question about adaptation, right? Like particularly once you look at a long-term future scenario out to 2100, you might start to think, okay, well, populations are going to be starting to responding to different thresholds because they're going to adapt as things change. I would argue that for ecological systems, that might not hold so truly. Like I think there's certain physiological limits that are likely more relevant. For example, in the case of birds, if we look at the underlying case studies that we cite that support the mechanisms we think we're finding, it's things about like dehydration, hypothermia that lead to direct mortality, and then effects on behavior and breeding. And so I think where those things are connected to physiological limits, it's less likely that we're going to have shifting baselines, I would say, unless there's evolutionary processes that we think are relevant, and then that's out of my area. I don't understand necessarily what the relevant timescales would be. I guess it's possible, yeah. But I think another thing would be to say that for this historical perspective, it's probably a better framework for assuming these fixed thresholds. If we start to look at long-term future ones, maybe then it would be something that would be really worth thinking about, actually. Yeah. So no, thanks. Good question. Cool. Yeah. Next. Yeah.
Great talk. That was really interesting.
Thanks.
This might be a bit of a naive question, a bit controversial.
Go for it.
So a lot of the attribution work comes from the physical
sciences,
right? Which was very important early on in the IPCC to make sure that we could attribute the warming to CO2 emissions, to what we're doing. Now, when that work has sort of in the scientific community is well accepted.
Yeah.
And we know that almost all of the warming and increase in heat waves is because of anthropogenic climate change. Is it worth the effort doing this? Like you could have got a lot of the sort of really interesting, or some of the really interesting things out of it, which is that tropics might be more impacted than temperate areas, and the importance of extremes rather than averages, from not taking attribution
and just looking at the historical changes
just
on the road.
historical change. And I'm just wondering
what's the added
what
value?
it adds. I mean, it's nice to link it directly to climate change, but I'm just wondering, is that do we still need to do that?
No, great question, really good question. So in this modelling context, I think one place where it's potentially would become more interesting would be if you start to look at variables that don't have such a substantial climate change signal. So when you're looking at precipitation, where the interannual variability is much bigger on decadal timescales and things, and you would start to have potentially trends in your data that might be substantial over, say, 1980 to 2020, but aren't actually, that you might not be able to tie out and link to climate change. So heat extremes is an example where this seems least necessary, because it's one of the examples where the signal of climate change is strongest. But there will be examples sort of on the range of spectrum between heat extremes and other climatic conditions where I'd hope that this kind of attribution framework would start to tell you something about, okay, well, you'd get a different answer essentially, basically, if you did this assessment with global temperatures, try and attribute what's connected to human emissions rather than just looking at the changes. Another thing is that would be to do with the uncertainty as well. Like if we, like on these estimates, there's an uncertainty there that's also coming from our assessment of how much humans have contributed to the temperature extremes, and it's kind of a technical point, but that's going to be larger once you start to take that uncertainty into account. And again, I mean, so the people I work with are mainly physical climate scientists who really love to talk about the distinction between internal variability and forced changes, so changes forced by human emissions. And we've started to do some work kind of testing these attribution frameworks on, if you're familiar with large climate ensembles, where you have the same climate model, you run it 1,000 times with the same forcing but different initial conditions. And it's really interesting, if you look at these kind of attribution frameworks, you can get very, very different local signals under those different realizations, which kind of tells you a little bit about the fact that internal variability does play kind of a role. And so for the broad picture, it probably won't matter too much. Definitely not for temperature extremes, but for other variables, it might more. And with sort of local context and for uncertainty, it might be relevant. No, great question as well, yeah.
This is absolutely fascinating. Thank you for
Oh, cool.
the response. But in particular, it's so fascinating to see, despite some of the limitations you noted with the data, how much you were able to get from such longitudinal studies, because that data feels like it tends to be very sparse.
Yeah.
I'm curious, now that this model has sort of been developed, does that change the requirements over how much of a time frame you'd have to cover in order to now apply this? For example, when you were talking about these desert biomes earlier, if those weren't falling within this original data set, now that you have the models, could you do that on things that don't have quite the same time?
Yeah. So I guess there's always if you've got less data, it might work if you've got a strong signal kind of thing, right? So it'll depend on the system. It really depend on the system as to whether first of all you'll actually pick up the effects in this stage, in the statistical modelling stage with the historical effects. That would really just depend on the balance of the signal and the data availability. One thing to say, because you've asked the question, one methodological point that I didn't touch on here, because it's more detailed, but it connects to this issue of balanced data coverage. So one thing that we do, because for these different bird populations, not all of them have got data all the way from 1950 to 2020. Yeah, it's very mixed. I think our average length is, I think the median is 30 years and the average is 20 or something. It's pretty good, but there's definitely big data gaps. So what we do before applying our attribution analysis is we do a basic interpolation, extrapolation of the abundance data to get a baseline. One important thing that we do is we explore very different assumptions about how to do that extrapolation, and we always get literally the exactly same numbers. And the reason for that is that all of our effects are going in as a percentage effect, and then we estimate them as a percentage effect again, so the baseline essentially doesn't matter. But that's just to say that there are those issues with data gaps, and we have to account for them somehow. And I guess that will get harder and harder the less data that we have. So it also is also a case about like how much do you want to generalize from the data. If you've only got data for 5, 10 years or something from a few desert areas, do you want to then do a study that like, I don't know, says like this is the effect in the tropics or something? Like even this is probably like, yeah, people would probably come and argue with me and be like, yeah, well, come on, you're really not getting that many populations. So I think it's possible, but then it'll face limitations in terms of statistical power and also in terms of generalizability. Yeah. I think. Yeah, great. Yeah, okay.
Lots of thanks in the chat
Cool.
for a great talk. James has got a question for you. He's also saying it's a naive question. How accurate or trustworthy are extreme event forecasting efforts, and can these be used in planning efforts or future vulnerability assessments?
Super good question. Yeah. So again, some of the people I work with at this Barcelona Supercomputing Centre, they're really interested in what they call as like decadal prediction, climate decadal prediction, which is closely related to forecasting. Because the thing is, so climate is predictable on long time scales, like multi-decadal time scales. There we can talk about the distribution and how it's changing, but from year to year, like we start to get into the context of essentially weather prediction rather than climate prediction, and it's a totally different game. And the chaos of the system is much more dominant at those short time scales. So forecasts become much more challenging. From what I've understood, there's some skill at like seasonal to sub-seasonal timescales for general metrics of temperatures like with all these things. In the thermodynamics of the system, they can predict things. And once it gets to talking about the dynamics, the precipitation, the atmospheric dynamics, it gets super hard. But yeah, so at seasonal timescales, maybe yes. And I know actually that there's some ongoing collaborations between the BSC and I don't know if you've seen this literature on like, it's from a group in South Africa about like climate exposure and risks to ecological systems. There's one it's like abrupt transitions of exposure. Yeah, Anthony says I think it's closely related to some of the work you've done in marine realms. And they're trying to collaborate by putting some of their models with these decadal prediction systems to say like, can we give risk assessments that are maybe more on timescales that are more relevant to managers, like 5 to 10 year timescales. But it's challenging. I think we've got a workshop on it coming up in the autumn, and I'm not really sure how much. I think the ecosystem people, they're going to be surprised at how little skill they'll get from these decadal forecasts compared to just the general projections, because it's really challenging. Yeah. So I think there's potentially scope, but it's a really difficult area actually. Yeah, Matt.
I have a kind of question building off what Ant was saying, which is the percent, what you're showing at the end,
Yeah.
percent of the total population change climate,
Yeah.
of that, only 20 to 40% is attributable to humans.
No, so it's really saying no, it's not of the percentage that's from climate, it's from humans. It's really saying the difference between what we've observed the birds to be to what we think the birds would have been at in a scenario without any climate change. So it's kind of like all of the long-term climate effects are in there.
So then, because there wasn't too big of a difference between attributed to climate or attributed to human-driven climate.
Yeah.
And that's what you'd expect because humans are the cause of the climate change.
Yeah.
Okay, got it.
Exactly.
So okay, that checks out. I had another question. When I was interested in the migratory bird part.
Yeah.
If I'm a migratory bird and it's super hot, I'm not stopping. And so my question is, when you extracted the heat extreme, did you line it up with the time the migratory bird is in the area? So for example, there's heat extremes in January, the migratory bird showed up in March. They might not even know it. They don't know what happened.
No, super good question. This is part of what we were thinking about in this when trying to do this analysis as well, and we realised that was a bit of a limitation. We're limited because Living Planet doesn't record when they observe bird population. So kind of surprising. Other data sets do, like like we've been working with riff fish in the context of with HAR and stuff, and they've got actual dates of when the population was measured. So we just couldn't do that, and we had to just assess exposure over the whole year as a metric. One thing that's interesting is then that we do still see an effect. There's bigger uncertainty, which probably reflects these kind of mechanisms. But I think there's also potential mechanisms via which temperature exposure to the ecosystem could still affect the bird population, even if they're not there at that time. Like if it has impacts on like insect abundance, food and things. So that's like one possibility to interpret that as well. But it is a limitation for sure.
Yeah, okay.
Yeah, Ash.
Yeah, they're really looking to, I think we could chat about afterwards. On that point, actually, I mean, you don't know the exact date that they would leave, but you could do parts of the year, like you can split the year in half and just take that off. You could test it a bit that way, but my question was about, in the top of a lot of red lists.
Yeah.
The red list at the start, did you, for these species that appear to have large impacts, did you check in their red list assessments if they have climate change as a threat? Because I think it's really hard. So I've got a lot of data I've used is on that, but I think assessors vary in how consistent they are. It's quite hard to prove that climate change is a threat, and even harder to prove is the deterioration in status. So there's sort of two levels.
Super interesting question. Yeah, we didn't look at that. We definitely could, but again, I think there would be some limitations with how we would be. I think I would have concerns about how we would be applying our model there in terms of drawing too much from it. Because again, if you think about the actual modelling framework that we're doing back here, it's this kind of mixed effects modelling, which gets an aggregate response across the populations within a given group. So it's not going to tell us so much really about how individual particular species are responding. It tells us about how all the species in the tropics are responding, essentially. And it shows us that on average for the species in the tropics, there is an aggregate negative effect, but not that it's one or the other. So when we see all these differences in this kind of figure, it's kind of like they're mainly driven by these aggregate heterogeneities. They're not driven by like a very species-specific effect at that location. Having said that, so I mentioned that there's a sort of ongoing collaboration with another colleague where we're using a comparative extinction risk modelling, which uses the IUCN red lists as its predictor variable. And then, yeah, I'm sure you're familiar with those things. Then you like map different risks in the range area of that species and try and predict the different categories. And in that context, I think this framework could go more towards what you're kind of describing, because yeah, you have your very specific data for the species. It's still like a broad model, but normally it's like these machine learning models like random forests or something that are predicting it. And we were hoping to try and start to see. We were doing this for the trees. We've managed to get like a decent predictive model on the IUCN red list, and then what we've been trying to do is like do the same with the droughts. Be like, okay, let's try and produce a counterfactual of what would the red list statuses have been if the droughts hadn't intensified the way they did. From what I remember so far, we've got similar numbers of overall species that have been listed, like uplisted, and that they say it's because of climate change. We haven't done the full analysis of like, is it all the same species? But I think that's quite a cool context for trying to do that. Yeah.
Yeah, you could do with corals as well. So corals have been reassessed. Well, like warm water reef corals, which to a coral expert, what is horrible to hear. It's a random group across different families and things.
Yeah.
But they have reassessments in that. The majority of those were because of climate change.
Interesting.
So,
Yeah.
so that might be an interesting group to look at.
Do you know when the reassessments were? Like what the time period was?
No, I can find
No
out.
idea.
It's like they're all the groups that have been reassessed are all between 1980 and
Amazing.
present.
Yeah, great. Yeah.
Corals just being redone now that they'll have 3 full different assessments. So you have 2 time points.
Yeah, great. That would be a really strong context, I think, to do with the thing there. Cheers.
Now, like there's lots of motivations to talk to Max more about this work. Max is around for the next couple of weeks, or this week and or next week. So hopefully that provides you all with an opportunity to catch up with Max.
Yeah, I'll probably go for lunch now. So if he wants to come, you're welcome. Cool. Well, thanks.